But I think we need to move on now and come to the graphs itself of the reactions, the graphs of the endothermic reactions and the graphs of the so called exothermic reactions. It is also called the energy profiles for a good reason. Let us just look why. If I go back to my screen now. If we look at a graph of a reaction again, remember your labels always, and we have our reactants, and we see we need to put energy in to break these bonds. Yes, we break those bonds and we need to put energy in. We call this part of the reaction the endothermic side of the reaction. Okay, so energy in is endothermic. Then we get our activated complex, and then we rearrange them, and when they form new bonds like this, we find new bonds or new arrangement, new substance. That is what the chemical reaction is, forming new substances from the reactants. We find here energy goes out when bonds are formed. So, literally this graph is an energy profile because it tells about how much energy comes in and how much energy goes out of the system, and that is where the idea of heat of reaction or delta H comes. In other words, the difference between these two energies is delta H. Also, what you need to know is we just focus in these diagrams on two sides. How much energy do we have at the beginning and to break it, and how much energy goes out, and whichever one is greater we call the overall reaction. If this one is greater, we call the overall reaction exothermic. If this amount is a larger amount than that one, then we call this an endothermic reaction. Maybe you do not grasp it, but just look at the next graph for you. Now, if I must ask you immediately without looking at the heading, is this an exothermic or endothermic reaction? We will say, okay, the heading says exothermic, why? Let me give you the short answer. This is the level of the energy at the beginning of the reaction. Remember, the reaction is progressing in this direction. So, that is the level of the energy. That is the energy at the end of the reaction. So, let us see how much energy went in, so much in, and so much out. This is the endothermic side, energy in, and exothermic side. Which side is larger? Which side is longer? Of course, it is this one. So, this is an exothermic reaction. But let me get you more details now. 1. Always take note that you read what is on this side. It will say potential energy, it will say sometimes EP, it will say at times chemical potential energy. Always make sure that you read properly what is here. 2. Always read this side of the axis. It will say progress of reaction, it will say reaction coordinate, it will say course of reaction, and all sorts of labels as the reaction goes. This simply means the reaction starts here and it goes in that direction. The energy starts here and the energy increases. So, from here to there the energy has increased. So, what do we have here at the reaction? What does that line tell us? That is the amount of energy, and we read it over there. So, number 3 tells us the amount of energy that the reactants have. Now, what do we do with reactants? We break the bonds, and what do we do when breaking the bonds? We need energy. So, we simply add energy in, and that energy goes up. The graph tells us that energy goes so far, and that amount of energy that we add in is called the activation energy. So, what is activation energy? The amount of energy that we need, the minimum amount of energy that we need to start a reaction, because as long as we are lying there, it will still remain reactants. What is the first step? Break the bonds, put energy in, and it's that amount of energy that we need to break the bonds up till there, and that is called the activation energy. And of course, we know by now that when these reactants come to the top, what do we call that number of loose, unstable, temporary atoms that's lying around that you cannot separate? It is called the activated complex, of course, yes. And now, the activated complex is now going to form new substances. That is the definition of a chemical reaction. And they will be called, the new substances will be called products. And while they are formed from activated complex to products, we find that energy is given out. So that is the amount of energy given out. That whole amount of energy is given out. And now the difference between where I started with energy and where I end, that difference is called the heat of reaction or change in enthalpy. But we normally use the word heat of reaction. Now, let us quickly see. So much energy in, so much energy out. That is positive. Activation energy is always positive to start a reaction. And this one is so much energy out. So which was more, in or out? Of course, we gave out more energy. You can see the long arrow. If this was a vector, you can see the long arrow compared to that one. So this is the difference between the two. And how do I get it? The difference between that line, that amount of energy, and that amount of energy. So it's always final minus initial energy. And that's the way I'm going to get it. And therefore, I then say, because I have a negative number, I have less energy. Let's say this was 10 and that was 50. It will be 10 minus 50 will give me minus 40. That's why I know that delta H, or heat of reaction, is less than 0. Okay. Now the next one I'm going to test you on to see whether you actually understand the next one. This is endothermic. I'm going to ask you to either send me answers, or you could of course also simply shout out answers wherever you are, because I'm trying to look on my screen now to see which schools have responded. And many schools say, what does bond energy mean? What does the activation energy have on the graph? What effect does it have? Okay, then maybe I should just answer those two questions. What's bond energy simply? The energy needed to break a bond. Bond energy, energy to break a bond, the energy needed. Okay, that makes sense. Next question, what effect does the activation energy have on the graph? No, activation energy is simply the amount of energy that we need to start the reaction. Remember, the reactants will lie there. Now we've got to break them to form new ones. So the first thing we have, put in energy to break them apart. And then once we've broken them apart, that's the energy that we need to start the reaction. So it's the minimum energy that we need to start a chemical reaction. Okay, make sure these definitions are on pages 1 to 4 in your notes if you have them. If you don't have those books, make a plan today. Don't complain. Go out and ask, where are our books? Get our books to us, because we are eager learners, we want to pass. Let's get back now to the endothermic reaction that we have on the screen, and I will do the questions for you. Number 1, what do we call this axis here? There are two possible names. I am not going to give it to you. You should know it by now. Number 2, what are the 3 possible labels we could put along here? And what does this axis tell us about? It tells us the steps in the reaction. Do you remember how many steps there are in the reaction? Basically just 2, bond breaking and bond making. Okay, and now number 3, what does this blue line tell us here? It tells us the amount of energy that the reactants have. Remember, this graph is also called an energy profile, so it tells us all about energies. What does this part of the graph tell us from here to there? It tells us the energy we have to put in to break the bonds to start the reaction, and therefore it's called the activation energy. Can it ever be negative? No, because you put in energy and it's always positive. It means energy into the system to start the reaction. Okay, next one. What do we call, by the way, the stable or temporary stable state of the atoms or particles in this reaction? We call it an activated complex. We can't separate it. We simply find it is there, and it quickly gets into either back into reactants or it goes to become the products. That's what happens. And what does this blue line tell us? The amount of energy. And where do we read the amount of energy? We simply go across here and see what number appears here, as you'll see later on. So, if that is the energy that I put in, then where is the energy difference? Energy difference is always final energy minus initial energy. So it's between that line there and between this line here. So what do we give, what label do we give to this one? Of course, heat of reaction. How do we calculate it? Final energy. That means I take that graph and extend it that way and I read it off there. Minus initial energy, energy at the beginning, I read it off there, and I will find that this has a positive value because it's a high value minus a low value. That's positive. And then what can I say mathematically? That delta H is greater than 0. That's the endothermic one. Now, let us quickly see whether we have covered everything before I summarize for you in 5 minutes what we've done. Basically what we've done is, I've said the following from beginning. When I had my reaction and I put in the magnesium ribbon into hydrochloric acid, it was heating up, and that's one observation. If the examiner asks you in the examination, what's your observation? You say, the test tube or the system or the experiment was heating up. That means energy was coming out of the system. If he gives you another one, he says to you, here is one that was getting cold, I can simply say, okay, that means energy was taken in from the surroundings. But my observation, what did I feel, sense? It was getting colder. Observation is simply using your senses. Not your science knowledge, your senses. It was getting colder. It was getting hotter. And that is my observation. And you need to read your questions carefully in the examinations. If you ask you, what do you observe? You say, I feel this one was getting colder. I noticed that. Or I measured with a thermometer and I noticed that the temperature was going down. Okay, that's your observations. And secondly, we then told you about to do calculations. I will test you now. And then lastly, we looked at these two graphs, which are very important for you to understand. All these labels you need to understand, and all the definitions on pages 1 to 4 you need to know. And for those that haven't seen the book before, this is what the book looks like. I'm going to leave it on the screen here so we can quickly have a look and see what this book looks like. It says Telematics, and at the back is where we are today. At the back of this page, and there we see are the graphs I've been talking about, and the heading says chemical change, and there are all the definitions that you need to know, and there's a discussion on it. It tells you how to calculate it, etc. And here is activity 5.1 starting, examples, activity 5.1 on page 4. There are the tables I told you about that you'll be getting. So I want you to complete these activity 5.1 on pages 4 to page 5. Just a quick summary for you on my screen once again. On my screen, this comes from the examination guidelines in 2009. It says what the learners must be able to do. If you haven't heard about the examination guidelines, make sure that you ask your teachers about this. It says the learners must be able to explain the concept enthalpy and its relationship to the heat of reaction. Enthalpy, the total heat content of a system. Okay, then define exothermic and endothermic reactions? Simply, either heat is taken in or given out to the surroundings. Identify that bond breaking requires energy, that is endothermic, and that bond formation releases energy, that is exothermic. Well, I've shown you those two steps. And then you must state for endothermic reactions delta H is greater than 0. The delta has been left out. And in both cases including the graphs. And then you need to know something about activation energy. What is activation energy? And explain a reaction in terms of two things. Energy is changing, but this is bond breaking and bond formation. And then you need to know what is the activated complex. Ask your teachers for a copy for the examination guidelines of 2009. You will find this there. Just a summary for you. Is this exothermic or endothermic? What do you think? Let me ask you quickly. I'm going to add magnesium ribbon to hydrochloric acid. Okay. What do you think what will happen? I will not go into detail because my machine will not run it today. Let me go to the next one. Do you recall the following? That during a chemical reaction there are two steps. The first one, you break the bonds. Energy is taken in, and that step is called endothermic. Step number 2 is when you take the activated complex with all the loose, unstable atoms and molecules, and you make new bonds and energy is released. And that step is called the exothermic step. Whichever is the greater, we call that the whole process that one. And here we have energy profiles. Let me ask you a quick question. We've got 1 minute to go. I'll ask you a very quick question. If you look at this one, let's say graph A, what is the activation energy of this graph, of the forward reaction? I went from this side to that side. Activation energy starts where? From a reactant to the maximum energy. That means 1, 2. So, and it is in kilojoules. So this answer is activation energy is 2 kilojoules. Then I ask you another question. What is delta H, or the heat of reaction? What is the heat of reaction in this graph? How do you do it? Products minus reactants. So it's 1 minus 3 gives you minus 2. What is the unit? Kilojoules. Okay. Let me go to number B. It might be slightly more difficult. What comes on this axis? Oh, the potential energy, AP there. What comes here? The cause or the steps in the reaction. What was the amount? What does A plus B mean? And what does C mean? A plus B is A, that is the reactions, the reactants. And what is C? The products. Now let me ask you 2 or 3 questions. What is the heat of reaction for this kind of reaction? It is the energy of the products minus the energy of reactants, or HF minus HI, which is X minus Y. There we go. Can I just ask you the next question? Is this an endothermic or exothermic reaction? This part is endothermic. That part is exothermic. Which part is bigger? This one, bigger than that one. Therefore, this is an exothermic reaction. Now for a very difficult question. What is the amount or the magnitude of the activation energy? Where is the activation energy again? From a reactant, putting energy to break the bonds to form activated complex, or enough energy to start the reaction. That means Z minus Y. Make sure you understand that one. Z minus Y. Okay, I think we have done most of the important ideas behind exothermic and endothermic. Let me remind you what they are again. Do you know what we mean when we ask for what are your observations? In other words, what do you feel, what do you see, what do you smell? Sometimes what do you taste? But we normally don't do that in a chemical laboratory. So it's normally what you feel, what you see, were there any color changes, was there any heat that you felt, etc. Those are your observations. Secondly, can you do the bond energy calculations? Simply break the bonds first separately, read it from the table, the values, and add it up. Then you take your bond making side and you read it again from the table, and then you take the last one, the final one, bond breaking minus bond making, and then you get your answer. If your answer is a positive answer, then delta H is greater than 0. It's a negative answer, then delta H is less than 0. Lastly, do you know your graphs? Do you know all your axes? Do you know the different names? Do you know the different labels? Labels like reactants, forward reaction, activated complex, products, delta H or heat of reaction. If you know all of those, then I think and you can look forward to the examination with great enthusiasm.